Greetings and welcome to another ReMBlock screencast. In this screencast, we're going to take a deeper dive into Yul and continue from where we left off in our previous screencast, where we just touched the surface and had an introduction to the Yul programming language that is used as part of Solidity Smart Contract development. So over in my remix editor, I've got a new smart contract here, which is going to be used to demonstrate how Yul manages storage and storage slots. So if you're familiar with Solidity storage slots already, you'll know that when you create storage variables, they are allocated into an indexed slot inside the actual smart contract itself. So if we declare this now, and we'll build a simple getter smart contract where we have a uint 256, which will store a value. And like that, if we set it like this, then it will be default to 0, as we know. And then I'm going to create a function that is going to be called setValue, and it will take a uint 256, which we'll just call v as the parameter that we'll pass in, and it will be an external function. And this function will basically set the value to the value passed in. Now, the next function I'm going to declare is going to be a getValue function. And this function will just simply return the value that is in the storage. So we just return the val. Now that is needing, this just needs a returns, and this will be returns a uint 256. Okay. Now with that declared, we can just take a look at that and see how it works. So bear in mind I've got auto compile checked here, so this is already compiled without any errors. And so we can go straight to the deployment. So I click deploy, expand the contract, and if I click get val, you'll see the value is 0, which is expected because we didn't set any initial value to it. If I set the set value val to 99 and then check the value again, it's 99. So there's nothing that is unusual here. This is all pretty standard, pretty basic Solidity code here that just gets and sets a value. Now, as you know, that if we had made this public, it would automatically give us a getter, but I just wanted to declare this explicitly to show. Now, how would we do this in Yul? Well, we can declare a function, and let's declare the function to get the value first of all. So we'll call this getVal Yul, something like that, right? So getVal Yul, and this is going to be the same type of function. It's going to be an external view that returns a uint 256, nothing different there. But what we're going to do in this case is, and actually I will set the variable here, I'll just call this R, which is the return variable. And I'm going to have an assembly block here, and I'm going to say R equals, as we saw in our last course here, I need to make it like this, right? So R equals, and then what? Well, let's try val. What happens there? We get a compiler error. What is it saying? It says that the identifier is expected. This is because of the semicolon. Doesn't like semicolons, right? Okay, so only local variables are supported. To access storage variables, use .slot and .offset suffixes. This is interesting. Well, what .slot will give us if we type that is, firstly, it actually compiles now, I think. No, there's still an error. It's this needs to be restricted to pure. Please forgive me for that. So yeah, so now we've got this function, but the issue is, right, and it compiles, but the issue is that .slot in this case gives us the slot or the location, the index location of the storage variable. And so as we know, when we declare storage variables in Solidity, they're allocated slots. And so the first slot is 0, and the second slot would be 1, and so on. So let's just, out of interest, let's just deploy this contract and see what happens when we call the function getVal Yul. So if we call this, we get 0. Now that is the same as getVal because it's set to 0 as a value. But really what this is returning is the slot location. And I can show you this by setting this to 99 again. And we call getVal, which returns 99, but getVal Yul still returns 0, as you can see, okay? And this is because val.slot gives you the slot. So how can we get the actual value that's stored in that slot? And the answer is to use the function sload. Sload, like so. And sload takes one parameter, which is the slot location. So if we pass that in to the function sload, then we can use that. Now, as you can see, we're getting compiler error again, and we now need to change this back to a view. Okay, so now we can see we can get the value. So just to recap, the dot slot gives us the slot location of the data, of the storage data, and sload takes that value, or takes a slot value, and gives us the value that is in that slot. So let's compile, and we can try this out again. So as before, the value is 0 as expected, and if we change it to 99, now 99 is returned from getVal, and it's also returned from getValue Yul because we're using sload. So let's continue with this now and add a few more slots to our contract. So I'm going to create a couple more slots here, val 1 and 2. And as you know, just to recap, this would be in slot 0, and this would be in slot 1, and this would be in slot 2. And I can set all these values this time as well. So I set val to equal 99, val 1 can be equal to 199, and val 2 will be equal to 188, for example. All right. Now I'm going to create another function here. This will be more of a generic function that will allow us to get a value by slot ID or slot index, let's say. And I'll call this slot index, and this will be a uint 256, and it will be an external view that returns the value, which will be a uint 256, and we'll just call this val. All right, we're going to use an assembly block as we have done previously. We're going to have our variable called val. Actually, we should call this something else. We'll call this return, or ret, just ret for now. Okay, so we call this ret, and we will set that to equal to what? Well, if you look at the previous declaration that we tried here, we use the function sload, and we want to get the value from the slot index. So we will use sload again. And what we pass in, well, we pass in the value that we passed into the function, which is the slot index. So we pass in the slot index here, and that should be enough for us to be able to use this function to be able to pass in a slot index corresponding to the storage values that we've already set in our contract. So let's try that out. It seems to have compiled okay, so we'll click deploy to deploy the contract, and then we're expanded out here. Now let's take a look at the function here. We've got get value by slot index. So if we use the value 0, slot, that means slot index 0, we get the value 99, which is this value here, because we got the slot 0, which is this value here. So let's try slot 1 and see what we get. And when we try that, we get 199, which is this one. It gives us the value of slot 1. Finally, we can check slot 2, and we get 188, which is of course this one. Now you might be wondering what happens if we do slot 3, which doesn't exist in this contract. Well, we get 0 back. In fact, we can type in any kind of arbitrary number and we'll still get 0 back. And really what's happening here is that the EVM basically looks at that slot, sees that there's nothing there, and just returns 0. So this is how we can dynamically fetch data from a contract by slot ID using Yul in an assembly block. Okay, let's continue on with this now. And up to this point, we've only been looking at how to get values by slot using assembly. So how about setting values by slot? Well, firstly, the first thing I'm going to do is I'm going to show you something that you can do which is not recommended to do in production. And the reason I'm showing you this is just to show you that it can be done and to be aware of this, so that if you saw smart contracts that do this, be very wary. So what I'm just going to show you here is the ability to set a storage value directly from it via its slot ID. So we're going to call this function set value by slot, so slot index and value. And we're going to pass in two parameters here. We're going to pass in the slot index and a uint 56, which will be the new value that we want to store. And this is going to be an external function. And what we're going to do here is we're going to write the assembly block here. And how do we set a value in Solidity, a storage value using assembly? Well, the answer is to use the Sstore function of Yul. And this function takes two parameters. It takes the slot index, where we want to set the value, and the value that we want to set it to. So we can see we're getting a compile error here, which is that we are shadowing a variable here. So we don't want to do that. So we'll just call this new val, all right. And I'll just call this new val. Okay, now that's fine. So what this does, as I mentioned, is it's kind of dangerous. It's because you can just set any value in your smart contract based on the slot index. And it's dangerous because you don't want to do this because you might create a vulnerability in your smart contract such that you could easily change the owner. So let me show you what I mean, right? So if I deploy this and we expand this out, then if we look at the set value function here, we can see, set value, this one here, set value by slot index and val. So it's this function here that we're looking at. So if I type in a slot index of 0 and a value of 777, now just before I execute this, I want to show you what the slot index of 0 is returning, which is 99. So that's the slot index here. Now if I set it to, if I run this function and call this now, you can see it's updated to 777, right? So I've just basically set the value here to a new value purely using assembly and literally by using the slot index as my reference point. And I can do this for every single value. So I can call this again with slot index 1, and we can say, let's say 888, and if we check it first, you can see slot index 1 is 199, but if I run that, it's now been overridden to 888. And finally, we'll try this with slot 2, and if I click that and check it, it's 999, it's been overridden. Now the other thing to note, and this is the point of one of the reasons why you wouldn't do this in production, is you can just pick an arbitrary slot, like say slot 99, and set that to whatever you wanted, 1, 2, 3, 4. And if I click the transact button and now go to slot 99, it has the value 1, 2, 3, 4. So imagine if that slot in your contract, let's say the slot was for the owner, then you could put in a new owner address, or you could zero it out, and you could basically do this to harm the contract or take control of the contract. So basically this is possible, but don't do it. And by the way, it's possible because this is assembly. So we're in a lower level programming language at this point. So you get a lot more freedoms, you get a lot more power, but you need to have a lot more responsibility. Okay, the next thing I want to show you is what happens when you have variables that are defined that are less than 256 bits. Because as you may be aware, in Solidity, variables that are that can fit into a word, which is 256 bits, are packed together. So I'll give you an example. Let's say we declare two more variables, but this time they're not uint 256, they're uint 128. And we call them, let's say, x and uint 128, and we call this y. Now I can write another function first of all that will get the slot of these of a particular variable, and we can make this pure because we're just going to return the slot, and we return uint 256, and it's a 256-bit integer, that unsigned integer that we're returning because we're returning the slot ID. So we call this slot, and we set this equal to, and what we're going to set it to? Well, in this experiment, if you like, I want to see what is the slot of variable x and the slot of variable y. So if we do slot for variable x, first of all, we want to set the slot to the slot of x. And if you recall, that is done by just simply doing dot slot, because any variables that are declared here automatically get these properties on them in the Yul contract that we code that we can use. Now we're getting a compile error here, which I think is related to needing to set the variable that we're returning here, which is slot. Okay. Oh, we're still getting a compile error. This time it's, I missed off the S here. Okay, that's it. So now we've got this. Now let's take a look at this. So what I'm going to do is I'll just clear out that old contract there and deploy the new one. And we'll come down here and we'll click on get slot. Now, what do we get? We get 3. Now, why do we get 3? Well, as you can see, val, these first 3 are in slot 0, 1, and 2, so this must be slot 3, which makes sense. And so x is in slot 3, but what is value y in? Slot what? Let's have a look. Let's just change this to y and recompile, which is done automatically, so redeploy, and now click get slot. What do we get? 3. So that's interesting. If these two are in slot 3, or basically in the same slot, then how can we use assembly to get the value of x and y if they are held in the same slot? So if these two values are stored in the same slot, then how can we read those values using assembly? Because so far we've been using sload as shown here and just passing in the slot index to get the value back. Now, in fact, if I set x and y values, let's say I set x equal to 1 and y equal to 2, and then I redeploy the contract. Now let's use this helper function here to get the value of slot 3. So we pass in 3 here and we execute that function, and we get this strange number back. Let me just put it here on the screen. It's like a huge number, but it doesn't seem to correspond at all to the values of x or y. So why is this? Well, the answer is because of the way the variable is stored. And let me show you how that is stored. So because it's packed, what happens is that the variables x and y are stored like this in memory. So we basically have the value 1 is stored first at the end, and in a 256-bit word, it would be stored with a 1 at the end here. But because they're packing, because Solidity packs these variables together, it puts the second variable here right in the middle of the word. So essentially what we have are 2 numbers that are stored like this. This is the 128-bit representation of the number 2 there, and this is the 128-bit representation of the number 1, but they're packed together into one word slot. So let me show you this as well. You can actually inspect this exact data as I showed you by simply changing the return type of this function to a bytes 32. If I do that and we redeploy and call the function again, passing in slot 3 as the slot we want to look at, you can see that it returns exactly that data that I just showed you. So that is basically how these 2 data are stored in a single slot. So how can we get these values out using assembly? And the answer is using a technique called bit shifting and masks, which we'll see a lot of this in Yul as you go through this course and through your experience with using Yul. So let's take a look at the way in which we can extract a value from a packed data set in a single slot. So here I've added some new data to the contract in the slot number 3. I know that these all get packed into the same slot because the total length of this in bytes is less than 32, and it fits into, therefore fits into a 256-bit word. And so what we have here is a uint128 with a variable name called A, and I set that to 9. We've got another one which is uint96 with the variable B set to 7, and so on and so on. As we can see, the variables are decreasing in size so that they get packed into the same slot. Now I've got this other helper function here called get slot and offset, and what this will do is it will return the slot as a uint 256 and also the offset of that slot that we're interested in, or of the variable in the slot that we're interested in. And so what do I mean by that? Well, if we take, for example, this variable here, as we know, this variable is packed into slot 3, so we can return the slot value by calling c.slot, and then we can call the offset by calling c.offset. So all of these variables here will also have an offset variable. So what does the offset tell us? Well, let's have a look at what the compiled contract looks like when we deploy and run that function. So if I deploy and expand, and then we call the get slot and offset, if we call that function here, we get these two variables back. We get a slot of 3, which is not surprising, but this time we get an offset of 28. So what does that mean? Why are we getting 28 back from c.offset? Well, what this means is that the variable that we care about, in this case c, is 28 bytes back from the left edge to where that data is actually located. So if we want to take a look at that, what we can do is call this function get value by slot index, and we can pass in 3, and what we get back is the full value in as a bytes 32. So let me just copy that into here and just show you what that looks like. And so what you can see here are all this data is essentially in this one data slot. So you can see the number 9 at the end here, and as we move to the left we see the 7 and then the 5 and then the 3, and the 5 and the 3 are packed closely together because they are smaller data types. And so we now know that the variable that we're interested in, which is C, is 28 bytes left of the edge. In other words, we can see here that C starts right here. So if we take a look at this, we can take that and I'll copy this into a terminal. I'll just start up Node, and I'll use Node to calculate the length of this, and I'll divide it by 2 because this is hexadecimal string, and so we get 28 bytes, right? So that means that this value here, the offset is correct. This is indeed 28 bytes, and then we get this value 5. So we can shift right by 28 bytes to be able to extract this value. So I'll show you how to do that. So I'm now going to show you how we can use shifting and masking to extract a value from a slot like this, which has an offset. So basically a value that's been packed inside a single slot. So I've got a function here which I've just defined called read slot3 var c. What does that mean? Well, I'm basically saying we're going to take the variable c from slot 3 and return it. So what am I doing here? Let me break this down. So we've got this variable, we've got this function which returns a uint16, and we are fetching it using assembly. And so let's do this step by step. So the first step is we use sload. Now we're already familiar with sload. Sload takes the slot that we want to load from. Now in this case we know that the slot of C is 3, and we're using c.slot to get that value. So this will fetch the value from slot 3, but sload only works in byte 32 increments, or 32 byte increments, right? So we have to deal with that. So increments of 32 bytes means that we get something much more than what we need. And in fact, this is what we get here. So I've just called this function here with slot 3, and it returns the bytes 32 of that. So essentially, at this point, value is set to this. And as we can see, this is a 32-byte word that contains the entire slot of data. Now, as we know, in the previous section, we saw that the value that we're interested in, which is C, is 28 bytes to the left of here. So it's located here. And so what we need to do is shift right everything off this and get this value such that this value here, the value we're interested in, is right at the end here. And so shifting right by 28 bytes means we basically take all of this and shift it off to the right. So what I'm going to do here is I'm going to do this quickly by just changing this to a 0 and this to a 0, and then I remove that out and place it here. And so if I put that down here, that's what shift right returns. So essentially what we have now in shifted is this. Now I want to just explain what this function does, SHR. It's the shift right function. And where does 224 come from? Well, essentially I just hard coded that because we know that the value that we're interested in, which is var C, is 28 bytes to the left of the edge, and shift right works with bits. So we just simply multiply 28 by 8 to get 224 bits. Now if we just flip over to the documentation here, we can see shift right is basically a function, or SHR, is a function that logically shifts right y by x bits, and x is the first variable, so that's where we need to put in the value of 224, which is the number of bits we want to shift to the right. So coming back to this, now we got shifted, which is basically this value. Now the last piece that we need to do is we only are interested in this last piece here, which is the last two bytes of this 32-byte word. And so how can we sort of extract or pull off the last 2 bytes like this? And the answer is to use AND. More explicitly, this is a bitwise and you'll see this pattern a lot in Yul, where you'll see like a sort of a bunch of Fs here, hexadecimal Fs, and then the value that we want to bitwise and so what this 0xFFFF actually is a 32-byte word with the last 2 bytes set as ones essentially in binary. Let me show you this in a terminal, how bitwise AND works. So I've opened up a node terminal here, and let's imagine we've got a hexadecimal value of, let's say 1234, which is in decimal is 4660. Now let's also take the FFFF value, which is 65535. Now let's say, for example, I want to bitwise AND 1234 with, let's say 00FF, so 0x00FF, and I'd use a bitwise AND, and in JavaScript it's just a single ampersand 1234. Now we get back 52. Now why do we get back 52? Well, the answer is simply wherever there is a 0, you can remove the number, and wherever there is an F, you can keep the number. And so we got first two, here we got 2 Fs, so that means we keep the 3, 4, and we got 2 zeros, so we drop the 0, 1, 2. So if I write that out, it would be 0034, which is our 52. So that, I think, hopefully makes sense. And just to be clear on this, the values are really bitwise, so we need to convert these to binary. So we can do that by looking at what the binary representation is of these numbers, by using toString and passing in the base. So the binary representation of 0x00FF is basically all ones like that. The binary representation of 1234 is this. And so if we were to do a bitwise AND on these two values, and we can do this also in binary directly by using binary literals like this in JavaScript, then of course we'll get the same value, 52. But really what's happening, and let me just copy this back into Remix here, and I'll just show you. What's really happening here is we are ANDing each of these at each bit. So for example, and actually what we need to do is pad this with zeros. So we are saying anywhere where there's a 0, forget about those numbers. And anywhere where there's a 1, keep those numbers, or keep those numbers the same, right? So what that basically means is I can put my cursor here and go down to the number that I'm bitwising, copy that, and I can paste that back into here and turn that into a binary literal, and you see it's the 52. So basically that's the bitwise AND of these two numbers. So if we come back to our working example here, what do we have? Well, we've got this number here. So what I'll do is I'll just copy this. I'll just copy the first few bytes here. So I'll get that. And that's a number that's quite enormous. And it's not the value of C, obviously, the value we're interested in. But if I bitwise AND with this, so I'm going to take this as well. And I'm going to do a bitwise AND with this number. We get 5, and that is the value of C. So if I run this, so that's basically what's happening here is with this bitwise AND, is it's ANDing in this way. And so if I run this function, so read slot 3 var C, so that is here, we can see that we get the value of 5 back. Now let me just show you something. If I was to make a mistake with this and I happen to put in too many F's, right? Well, let's flip back to the terminal again and just see what happens there. So take the same two numbers and I'm going to add 2 more F's. What happens is it ends up keeping all of the values here. In fact, it keeps this 3, so we end up with this number that's wrong. So let's try that and see what happens. Now we have to basically redeploy because I've changed the code here, but I'll redeploy it and I'll rerun that function. So get slot 3 and you see it still returns 5. Now why is this? Well, the answer is because of the way we've essentially casted back to a uint16 in the solidity function definition here. So it's taking this cval, which is bitwise masked in slightly incorrectly in terms of what we're looking for, but then it casts it back down to a uint16, which ends up resulting in the 5. Now obviously this could be a source of some difficult to discover bugs, and you can see this by changing this back to a uint256 and again, you know, recompiling and deploying and calling the function again, and this time we get this number here, which matches the number that we get back here in the console. So because we're bitwising too many bits basically. So be careful with this, of course, when you're using bitwise. Make sure that you include the correct number of hexadecimal representation of bytes. In this case, this is 2 bytes because we want to get the last 2 bytes, which is the last 4 hexadecimal characters from this shifted word that we get when reading the slot. So that's one way of loading a variable from a slot where the variable has been packed into a single slot, and we use offsets, we use shifting, and we use bitwise masking.